The system I'm going to talk about, let me just introduce. You all know everything about it. It's this. Okay, so we've heard quite a bit. What is that? Let me just put things in context. So,
it's a star out of focus.
Sorry?
Star out of focus.
Yeah, it's like such an explosion, but what you see nicely here is a fold of chalk running into the ambient medium. And then there's this is the ejector, there's a contact discontinuity and some reversal which you cannot see here. So let me just elucidate the structure a bit more. This is this is actually what happens at late stages. And so, so basically, I'm considering a relativistic explosion, and we've heard that already that there are some phases in the evolution. So there is a shock breakout phase, then it accelerates. Then of course things depends on how much mass is accumulated. But basically what I'm going to assume is that the ejecta at early stages reaches a highly relativistic velocity. And the structure at the early phase is something like this. There is a forward shock running into the ambient medium. This forward shock is typically highly relativistic, or essentially auto-relativistic. This is the parameter region considered here. And then there is also a reverse shock running into the ejecta. So this represents the unshocked ejecta, and this is a reverse shock here. And there is a contact discontinuity separating the two. And this contact is going to play an important role in this talk. So this is more or less the structure expected at early stages. Of course, as the forward shock propagates outwards, it sort of accumulates energy here. And decelerating, at some point, most of the energy is in the shocked. I call it shocked ISM, but it can be, of course, a stellar wind or whatever you want to not whatever fits my work, of course. So that's the thing here. So at some point, it accumulates most of the energy is in shocked ISM, and then you can forget about the contact and everything. Then the common wisdom now is that it runs into sort of the so-called blood-form decay phase. It's a very clean and simple system, and I'll question that. So that's the picture. So okay, so
is it supposed to look corrugated in the lateral direction or no?
Sorry?
Is it supposed to? Is there any meaning to the color in the shot?
No. Not yet. So just poor choice of. So actually, on my screen it doesn't. It's not corrugated. It's only here. That's interesting. Yeah. So it's a nonlinear process. This projector. So anyway, this is the late stage. As I said, there is just a forward shock running into the cell, and you can more or less forget about what's going on here. And so this is more or less the picture. Now, there are some open questions. Of course, this naive model, maybe not naive, but with this simple model, people try to explain everything. Flashes, afterglow emission, etc. And it seems to, actually provide quite a good model for what you observe. At least the late stage. We don't quite know what's happening in the early stage. But
why is gamma
no, it doesn't have to. So this is for blood chemistry solution with a constant potential.
Gamma squared.
Yeah, gamma squared. So what is the square?
Yeah.
Okay, sorry.
It
should be gamma squared. I think that you know what follow it will be this one. Hopefully. If not, then. Okay, so so there are some open questions still. And we've heard quite a bit about some of these questions during this program. So for example, what is the origin of the magnetic field in the ISM? In the shocked ISM region. Yeah. So we see emission, and Eli can tell you all about it. And of course, if you just compress the ISM field, and if you take a microgas as never expected, you get nothing. There's a Lorentz factor involved, but overall it's in a coding file, it's a factor of 2. So you need to amplify it somehow by orders of magnitude. And there are some ideas, like the Bell's instability, if you somehow manage to accelerate cosmic rays. And we've heard from Anatoly Stokowski all about it. So this is one. I think there are ideas how to solve this, but nothing really, I'd say, confirmed yet. Then, of course, this question of particle acceleration, which is related to this. And I'll suggest that sort of the kinetic simulations that people are doing are assuming, of course, the box is on a very small scale, it's kinetic scales, but still they're assuming uniform conditions, so some of the structures I find may be relevant to this question as well. And then there is this business with the optical flash. I think that if I try to summarize it, actually was expected to see optical flashes, and for some reason we don't see enough. Actually, we don't see them. So this is another question. What's going on at the early stage, where the reverse shock propagates in the injector? And then there is another question, which is the stability of the system, which is related actually to all the other questions I listed here. And this is the actual issue I'm going to discuss. So some work was done on the stability of the Dracon-Mickey solution, and I'll show it. It's very much relevant to what I'm going to say, but I'm not aware of any stability analysis, even linear stability analysis of the system at early stage, except for a thin shell approximation, which is limited as well. So this is something that is concerned about. And then there's also the question if the Dracon-Mickey is indeed an attractor. So I think it's still an open question. Okay, so this is sort of the questions that motivate what I'm going to say. Okay, so let me now discuss the stability. So actually this problem has been studied quite extensively in the non-relativistic case, and I'll show some results because it gives insight. Actually what I find in the relativistic regime is quite similar, so it gives good insight into the problem. So naively, if you have if the system is decelerating, you naively expect convective or Rayleigh-Taylor instabilities. Now, just to remind you what a Rayleigh-Taylor instability is, if you take a heavy fluid and put it on top of a light fluid in a gravitational field, then this is not a minimum energy state. It tends to grow fingers, it mixes. And traditionally, I think the Rayleigh-Taylor refers to incompressible fluid. So, but what happens is that eventually the heavy fluid finds itself at the bottom. So why we expect here a Rayleigh-Taylor instability? Because there is no gravitational field. So the point is that if the system is decelerating, then in the frame of the contact discontinuity, there is sort of an effective. This is, by the way, a very naive or intuitive way to look at things. But this is more or less what's going on. So in the frame of the decelerating contact, there is an effective gravitational field. And then, of course, depending on conditions in the ejector, you might...
Pointing the other way around.
Sorry?
Is it pointing the other way around?
No, it's okay. No.
If it's decelerating, then in the frame of the discontinuity,
It depends
the
on the pressure.
acceleration is this way.
It's
It was the heavy stuff.
Sorry?
So if it's the other way around, it's the heavy stuff below the light stuff.
It's no. It's
So it should be stable.
no. It's not. I'll show you. Okay. Show you
The heavy stuff is behind.
the heavy stuff.
No, it's a shock instability, which is heavy.
No, this is not because it is hot. Right. So the pressure is similar. So it's hot.
At any rate, I mean,
It's hot in front and cold.
at any rate, I'll discuss more. But I mean, it's really the instability here is really convective. So I'm sort of doing a global analysis.
What about convective?
Well, let's say compressible fluid. So it's related to, it depends on the entropy profile and the pressure profile, essentially. So, I mean, you can get some insight from this. So, of course, there are conditions where it's stable, but there are conditions where, but typically if it's decelerating, then it's unstable. This has been recognized many years ago, 30, 40 years ago.
So what's the density distribution in this structure?
Oh, I'm going to show you. I'm going to show the absolute solution which I'm using. I mean, the density structure in the injector depends on the condition in the stellar envelope and the Schumacher process, stuff like that. And it's been studied by, in a non-relativistic regime, it's been studied by Sakurai and people. And I'll show some. In a relativistic regime, it's been studied by Nakamura. I'm going to discuss this in a minute. Okay, so basically, as I said, it's actually this thing has been realized by this guy, Bull, how do you pronounce it? Already in the early 70s. And he suggested that there's, I mean, he did some 1D simulation, very naive 1D simulation, but he already identified that there is a regime of parameter space where you expect the convective instability to develop, and he actually suggested that this may explain the structure of Young's supernovae. It turned out to be true. Okay, so so to get some insight into what's going on, let me show what people did in the non-relativistic case. So first, what I'm showing here is, so first let me say that in the non-relativistic case, there is a self-similar solution for the entire structure. And it's been studied by people like Roger Chevalier and also others.
You made self-similar solution to the turbulence that evolves, or
No. So the amplitude solution, like a platform solution, but for the system of the forward and reverse shock and the codec. So there is. I don't want to discuss it here because I'm going to discuss the relativistic case in a bit detail. So it's very similar essentially. So I just want to show the result because it's basically very similar. The advantage here that we also did a full 2 and 3D numerical simulation, and you can see how the nonlinear regime evolves. All I did is linear stability analysis, and I find instability. So at some point, one has to do simulations. But you can get, I mean, you can get an idea from the analysis what are the requirements for the simulations. So basically, I just want to show the general property of this instability. So what Chevalier did, he did a global linear stability analysis of a self-similar solution that he found a few years back, earlier. And what he found is that the system is unstable. I mean, it's stable for mode which has an order L, where actually the perturbation of the can be written in this form. So some dimensionless amplitude and a YLM factor. So these are the modes. And basically, so this L number is the YLM order, or the order. And he finds that the system is stable for L numbers smaller than some critical value, but then the instability sets in. And what is plotted here is beta. Beta is the gross rate. The gross here is, of course, algebraic, because it's a self-similar solution. It's not. It's exponential in ln t, actually, which is the actual right parameter to use. So essentially, as you go to smaller scale modes, yes, the gross rate increases. Okay. And you find a quite significant growth for L numbers. So the system is unstable for these modes. And you see here that a mode which has order smaller than this critical number are stable, essentially. And so the conclusion is that the small scale structure should grow first, grows faster, which is actually what you see in just in the very simple Rayleigh-Taylor instability. And the scaling is not exactly the same. And also, the growth rate is quite significant, so it should reach a nonlinear stage quite early on. Okay, so this is a summary of the linear stability analysis he performed in this paper. And then he did also 2D simulations, full 2D simulations, hydro simulations, and confirmed this result. So he indeed saw small structure going first, and then but it's quickly saturated in a nonlinear regime. But it was limited by resolution. So And then later on,
So beta is real.
yeah, here it's real. Okay.
It's real. There's no.
This is the real beta, if you want to.
But there's no imaginary part to beta.
In the class of solutions presented in this paper, it's real. Okay. But I'll show you that. Okay. Now, one thing I'll mention is that he was lucky because in the relativistic case, there are self-similar solutions to the perturbation themselves for all modes. This is unfortunately, so my hope was that, of course it was a stupid hope, my hope was that I might find the same in the relativistic case, and of course, if you come to think about it a bit harder, it's not the case. There is a scale that essentially is a boundary condition that the show breaks self-similarity except for the spherical case, but I'll discuss it in a minute. So here, essentially, his solution are essentially analytic.
So, but can you explain why you don't have any imaginary part? Because if you look at the simple, say, a uniform ejecta, like in the set of Taylor solution, you look at the stability of the set of Taylor case, you have essentially three regimes on the large scale which are stable. At the point where the wavelength is short enough so that the sound crossing time across the perturbation, okay, is short enough, then you get oscillations because on the time scale that the perturbation grows, there's sufficient time for sound waves to cross across the let's say the maximum and minimum perturbation regions. You always get this oscillatory behavior. So how do you avoid this?
I'm not saying there are no solutions to this type here. I don't think he, but he found essentially what happened is that here the perturbation propagates from the contact. You see, I mean the largest growth that is at the contact, and it's a bit of a technical issue, but and by the way, as I said, you are right. In the relativistic case, that's what I basically find. It's right. It's oscillating.
So I don't understand how you can avoid it here. Somehow you. So the growth rate grows so fast as you go to short wavelengths, so that perturbations never have time to.
Well, I mean, once at some point you reach nonlinear regimes, of course, all this analysis is irrelevant.
No, but in the linear analysis, you mean that the growth rate is so large that so the growth of the perturbation is always faster than the crossing time along the.
Right. Well, like for example, in the Riley-Taylor, it's also the case, right? It's very naive.
But it doesn't seem so from this plot because it's a logarithmic L, right? So.
This is L of 1000.
Right. So you change L by several orders of magnitude. Beta is changing not so much. So at some point, the different regions of the perturbation should be able to talk to each other. And then we must get some oscillation.
So.
Okay, it looks weird.
It looks weird. But I mean, I checked it. You do get this solution in the non-relativistic case. Okay, so okay, this is a linear analysis, and then later on there was a paper by Norman, and actually several papers by Norman in his group, doing a full 3D image simulations. And so here you see the result from one of the papers. And basically they confirmed that first they checked in the linear regime, they compared their solution with the Chevalier analysis to find quite good agreement, but at some point, of course, the solution deviates from self-similarity, etc. But what's more important for me is to show what is the structure of tail. So here in this sequence, this is the coordinate here. This is the forward shock, and this is the reverse shock. Okay, and as you can see, and time goes in this direction. So this is already and what you see, what they find is that this very quickly this Riley-Taylor fingers grow from the contact. Okay, as you might expect, and actually, as they increase the resolution, they see finer and finer structure, which is also what you expect. But what they say is that these fingers quickly saturate by the Kelvin-Helmholtz instability. So essentially this motion of the finger with respect to the shock medium produces a Kelvin-Helmholtz, and so you get this vorticity generated. I mean, you see all this. And what they find is that this vorticity also generates amplifies magnetic fields. So they find significant amplification of magnetic field around fingers. And also, and the global, I mean, the average field in the whole region is more modest. So they reach, if I remember, the magnetic energy in the simulation reached about 0.5% of the turbulent energy. But as I recall, the claim was that they are limited by resolution. So they weren't, they claimed that they are not convinced that they converge. So it could be that if they will increase their numerical resolution and actually find higher values. So it was an option.
The sum. So in this case, the resistivity and viscosity are completely numerical.
Yeah.
So the statements about the level to which you amplify the field is...
Okay, so that's this, right. There are issues here, but
So what is the initial density profile?
in this simulation, so I think the initial look here was, if I recall,
Can you sketch it on the board?
no,
Just sketch it.
they use the self-sim. I think at least in, I'm not sure if this is this, but I mean, they use the self-similar, I think, profile as the initial.
This maximum value.
But it's in the paper. I can check it.
Corresponds to the maximum value.
Sorry.
So it looks like initially there was a shell of dense material, not just a contact with continuum.
Well, there is an ejector, of course. It starts with
And so where is the eject?
this is the reduction.
Is it a shell?
Well, it's
It's
yeah,
not sharp. It's not sharp.
because it. Yeah, I mean, it's not a good reproduction. I can show you in the paper exactly.
But the density gradient has to be shallow, right? Because the shock is decelerating.
Sorry?
The density gradient that this is going into has to be shallow. Is it constant density or something?
In this
Constant
simulation?
density?
Yeah, they checked both constant density and I think wind.
Yeah.
Yeah,
But for the ambient, you mean?
but
Right.
the important thing is that
Decelerating.
it's shallower than 9 to the minus 3. So
Right.
it's
Yeah.
Otherwise, it would be.
Well,
completely
this is no relativistic actually, all this, right? But you're right, I mean, I'm going to get to this in the relativistic case. In more detail.
I mean,
The important thing is it should be decelerating, and indeed, okay, if you mentioned this, they run it long enough, so until I think the remnant is about 1,000 years old, and they find that it's very sensitive to the deceleration, so to the parameters, indeed very sensitive. And also, once the reverse shock crosses the shell, the ejector, then the sort of instability weakens.
It should become stable then.
Well, it weakens and eventually, well, they didn't run it until it becomes stable, but then you'll see that it weakens.
The decelerating cell of terror are stable.
Okay, so so basically, you see that the structure grows and eventually fits. So the conclusion here was that, and then they have some papers comparing this to observation, but I think that they would.
I want to go back to the question of magnetic field, because the analysis by Chevalier did not include magnetic field.
No, it's purely hardware.
Right. So I mean, I'm just thinking, conceptually, when you put here by hand magnetic field, right?
Well, they put a seed field, and what I'm saying it gets.
Qualitatively, this will act first to reduce, I guess, the stability, but then you said that some part of the energy will be transferred to the magnetic field. If I got it right.
Well, the magnetic field we heard. This is already talked about. I mean, the magnetic field gets amplified by it's getting wrapped around by this.
But first, they add magnetic field in the.
They start with some seed field.
No, but I mean, if you let's say that you put like very strong magnetic field, so you're
very
increasing,
strong. Okay.
so you're increasing the energy density.
You put a strong magnetic field where?
in the upper
In the ejector?
yeah.
So okay, that's of course if the ejector is too strongly magnetized, the whole instability is suppressed. That's what you expected.
Yeah.
So-
That's what
But that's not the case they studied here.
so here they just put.
The magnetization is, yeah, they put the subsede field,
Mhm.
which is weak enough. It doesn't affect instability. And the claim was that it gets amplified here. That's the claim. And it's quantified. I told you it's about 1% or a bit less, 1% of the. That's what they state.
I mean, I think that, isn't it just a very simple, we get instabilities when the pressure and entropy gradient are in the same direction.
It's more or less true, yes.
So, so for the simple, I think everything could be simply understood by this. If you
It's
take
not
the-
quite, because the global, I mean,
let me just say that. So if you look at just at the decelerating set of Taylor solution, the pressure is growing outwards because this is why it's decelerating. And the entropy grows inwards because the shock was faster at earlier times, so the fluid that was shocked earlier has a higher entropy. So there the pressure and entropy gradient are opposite, and therefore they are stable. The decelerating shock waves are stable. Now here, what happens is that you add something which is not so similar, this ejecta that was not shocked before, and the situation would be unstable. The pressure again is growing outwards because it's decelerating, and it would be unstable if the entropy of the shell,
so, I mean,
of the inner shell is lower. So if you add a cold, if the ejecta is a cold dense shell, it would be unstable. But if you put a hot shell,
even if
a
it's
high
cold,
entropy shell,
even
it
if
would be
it's-
stable.
Even if it's cold, so they analyze this actually.
No, if it's cold, it's unstable. If it would be
No,
hot,
even if it's cold, if it depends on the density profile of the unshocked ejector. They have cases where they show that, I mean, because the dynamics depends also on the, I'll show you the realistic case, but the dynamics depends also on the density profile of the unshocked ejector. So they actually have cases where it's cold and it's stable. Right? So,
okay, maybe you can play with the,
well,
with the
this
density, but
may
in
not be
general-
physical, yeah, but
It's
I
not
mean,
so in general, if you put a cold ejecta, it would be unstable because
in general you're right,
the
but
entropy
what
is
I
low.
want to stress is the
And all the rest is some.
But this,
all the rest
this
is details. So.
these arguments are local. I mean, the analysis here is global analysis. So it's global dynamic modes. It's so you get an insight if you do this, and basically you're right. Yes, when the entropy profile and the pressure profile are in the right.
Sorry.
Okay. Anyway,
All the rest is.
anyway, that's what you get. And I guess that these guys, in a lot of times the case, well, I said 20 minutes, right? It's not working well because of and they would associate this flumpy structure that you see in supernovae like this with this finger-defined stimulation. So this is sort of the general picture. Okay, so what happens in the relativistic case? And so, okay, I did a similar analysis for the relativistic case, and because I mean, naively you might expect that it will stabilize things. It's not clear. So what I'm going to describe now is only very preliminary results of my linear stability analysis. So to do the linear stability analysis, you first need an upper tube solution. And it turned out that there is a self-similar solution for the system in the relativistic case, which was actually derived by this guy here. Very recently. So this is what I used as my unperturbed solution. And then as I said, I did the global dynamical analysis.
So this is an extension of Chevalier's work to the
Yeah,
relativistic
it
case. So it's a shock plus a contact plus a reverse.
Yeah, I'm going to show it, but it's extension of Chevalier, but it turns out, to my that it's actually not a trivial, it's not a trivial extension as, even, had I knew this, I probably wouldn't start looking.
But is it really self-similar, the structure, where when you have a thin shell colliding with the external medium in this initial phase where the reverse shock crosses this shell? Is it really?
That's another question. But this guy is actually they have all kind of models for shock breakout and supernovae, and so they claim that the outer part of the ejecta in certain cases, it depends how.
Okay.
Well, you probably have to assume that the ejector is not a simple thin shell. It has to have some power law density.
You know what? I'm going to discuss the.
You have to choose some. You have to choose some nice ejector so that it will be self-similar.
Yeah. Okay. But
which is not right, because in reality you have a scale.
But my point is that I don't think that the instability itself depends that much on whether it's self-similar or not. I mean,
Exactly. It just depends on the direction of the pressure and entropy gradients.
But you still want to find, you know, to identify the gross and everything. So I mean, but to do this analysis, I had to use something. So this is the amplitude solution, just since you asked. So basically, the ejecta is in their solution is a freely expanding ejecta. So there is this velocity, and the density profile is just the power law in the Lorentz factor of the ejecta. This is referred to the entropy. Now, this index n, so they identify some cases from simulations they are doing. So this index n depends on, you know, as I said, on whether the stellar envelope is convective or not, things like that. Now, the instability, as I showed, does not really depend on details. It depends mainly on this m number, which on the deceleration. So it's not terribly. I mean, I can use the parameters to identify regimes. Okay, so this is the ejecta, and the ambient medium is as usual taking the density profile, which is some power, or kinds of free parameters. So n and k are free parameters. And so then,
So you see here, this is not just a thin ejecta. It's
well, I mean,
it has some.
No, it can be. I mean, it can be. As long as as a reverse shock propagate in this structure, it's of course it.
Right.
The row ejector.
I mean, this is self-similar solution. That's
The row ejector was initially
The question
constant.
is how representative this is of a real situation where you have roughly, if you have a roughly uniform density, uniform velocity ejecta, it would not be described
uniform
as-
density in which frame?
in the
Yeah.
proper frame.
So I think if you take, I mean, right? If you take n to be 0, so isn't it that
No, because V goes like R over T.
R varies from what?
Yeah, yeah.
From 0 to T?
Yeah, so, right, it's not a thin shell. You have an extended ejector with a power loop because you don't want to have any scale in the problem, otherwise it would be self-similar. And the problem
So basically the flow is not relativistic everywhere except the very end.
the very edge of the
I
shell.
guess it still applies until the
Ah,
shock
yeah,
hits the bottom of the
It's-
shell.
So the
because
picture here is,
physical
yes.
principle.
Well, I think the basic result would be again just depending
Well, I mean,
on
you can
the ratio of
take this
entropy.
ejector to be between gamma max and gamma min, of course. As long as your reverse shock is in this region, I think this self-similar solution is still okay. Yeah, once it crosses, it's of course finished. So that's the context here. Okay.
But still, you need the gamma to behave in a certain way in order to.
Okay.
with
So
radius. Otherwise
let me
it
show
won't-
you what you can infer from this. This is still the amplitude solution. You know what you can infer about the properties of this. It's also, as you see, quite limited. The solution. So first of all, because it's self-similar, this gamma refers to the Lorentz factor of the forward shock, reverse shock, and contact. Okay. Of course, they all evolve at same time evolution because it's self-similar. So it is index A which quantifies the dynamics.
Is this solution only valid in the ultra-relativistic regime, or it's supposed to be valid also close to the...
No, it's the what do you call? I mean, the forward shock.
Gamma, yeah, much larger than you.
Yeah, the forward shock is ultra-relativistic, and the reverse shock, I'm gonna show you. Actually, you can see that this is the trajectory of the reverse shock. So you can readily infer what is the Lorentz factor of the ejecta at the reverse shock, just after the reverse shock. And it's related to the Lorentz factor of the reverse shock through this relation. So it's essentially, the reverse shock here is quite weak. I'd say. I mean, depends on them, but I mean, these are all measured in the frame of the ambient medium, okay?
This should depend on the ratio of the densities.
not in the subsimilar, I mean, well, if you assume the velocity of the ejector, velocity profile of the ejector, then,
I don't understand it. If I take the density of the ejector to be, if I take A to infinity,
well, the subsimilar solution inside depends on this, but you're right, but I mean, you see, once you take this velocity profile, okay, and you know what's the trajectory of the reverse shock, it just determines the relative velocity between, so it essentially determines the velocity of the ejector and the frames of the reverse shock. Now the jump conditions, so the jump condition depends on the property of the ejector, of the mass. It's for the pressure and everything else.
so there's an assumption here basically that the reverse shock had already propagated deep into the ejector at a point where the density is such that the shock is weak, but this
Right.
happens, and this happened before it crossed the thickness of the ejector. Because otherwise it will not be relevant for us. In principle, in what we're interested in, you can have two different limits, where the density of the ejector is very high or very low, and then the reverse shock would be either relativistic or non-relativistic. Here you make some assumption about it. So this applies only to the
The
case where,
subsimilar solution applies
only to
only
the case where the reverse shock is
is non-relativistic.
is non-relativistic.
Well, it's- if M, it depends on M. It can be mildly, but I mean, yeah.
non-relativistic,
It
which
only applies
implies,
to, I agree, that's why I say it's limited.
so it's limited to that part of
Yeah.
parameter.
That's all I can,
Okay.
yeah. I mean, you cannot describe the case of a strong air shock, reverse shock with this subsimilar solution. It's not
Exactly. So
subsimilar.
if I have a low density of the ejector, it would not apply. These solutions will not apply.
Yeah, actually, I still don't think, well, okay, yeah. Okay, so the picture here is the following. There is the forward shock. Essentially, the shock times M is described by a version of the Bluff-Mackey solution. Okay, the reverse, the shock ejector, here, because the shock is not necessarily relativistic, you have to solve the jump condition fully. So they actually, okay, they account for it's the full solution for jump conditions and everything. And then you get, and then your M number, this number, is related to the ambient medium and the ejector profile this way. So once you fix K and M, if it's a win or just ISM, whatever, the profile of the ejector, it fixes this M, as you expect. Okay, so, and the instability depends only on M, that's why I'm saying it doesn't really care these details. So that's how the solution looks like for this parameter. Well, that's basically what you all know. It's the Lorentz factor, pressure and density. And then the density diverges. I don't concern myself about this. It diverges the contact for this class of solution. But
What's density? Can't see the colors.
Red.
red.
It's the one that has a spike.
The red.
With a spike.
The density and pressure are normalized. Of course, the ratio in forward shock is to be,
I'm just a little bit colorblind, so if you just tell me which shock is
You're colorblind?
Yeah, a little bit. So I can differentiate between
You was
red and
counting.
blue.
What is this color?
No idea. Probably green.
Red, yeah, I see so.
Okay, good. So which one is it?
This is the density.
This is density.
Yeah.
Right.
This is Lorentz factor, and here I
Lorentz
take something like 100, and this is the pressure.
Okay.
And then I just normalized. The ratio is, of course.
So in this case, it is clear because you're talking about very high density shells, so that the reverse shock is not relativistic and so on. So you have a very low entropy in the ejector here because with very high density, the pressure is
Right.
almost uniform. So you're going to get an instability because the entropy is growing outwards.
Yeah. Okay. So I have a remark. And you're right. If the shock ejector is too hot, then that is a quantitative question.
But if I take a low density ejector, it will be stable because the
Then
entropy-
it's a quantitative
Depends
question.
on the-
Eventually,
yeah.
it will be stable. I agree. And
also
also, if
the
it's
high density
magnetized.
ejector, it will be unstable because of this.
So okay. So but let me then. Okay. So. So as I said, this is the top solution I use, and then I just did the linear stability analysis on this solution. And so the perturbation is usually at this form. So that's the, so I look at the evolution of modes of order L. Okay. And there is an important point here actually. What they did in the isotope solution is that actually they matched two self-similar solutions and the contact. And that's what determines the ratio of Lorentz factors. Okay, so here it's quite similar. For the perturbation, you do the same. You match two solutions at the contact, and that's what gives it instability. It turns out it's the coupling at the contact, and that's also what complicates life. But so basically, so what I did is it turned out that in the spherical case, there are self-similar solutions for the perturbation. Unlike the Newtonian case, this is not true for any other mode. Actually, no. So I used this spherical solution was important because I used it both to test my code, and also I used it as initial condition. You need some initial conditions, so I used this as initial condition for my evolution of higher order modes, basically. Okay. But it's, actually you can use other initial conditions. So, yeah. So let me just mention this point about the properties of perturbation. As I said, the reason why they're not self-similar, you can see here. This is one boundary condition at the shock. Essentially, the perturbation equation have boundary conditions at the two shocks and two boundary conditions at the contact. This is a bit technical, I don't know. But now, if there is the perturbed solution has also a transverse velocity component, of course, because the shock becomes corrugated. And so the boundary condition of the shock gives this relation. Do the same constantly. So you can see immediately that, and this depends on time, of course. It goes like t to the minus m. So you can see, already see that it breaks some similarity. This is the time evolution, and this is a different time evolution. So, once I realized that I was quite disappointed. Anyhow, so I'm going to show the results and finish because I think I was planning on a much shorter presentation. And so I emphasize this is preliminary. I still haven't investigated all what it needs to be. But I can show you some results. So basically, as I said, the spherical perturbation with L equals 0 decay algebraically, and you can actually, if they have this form, t to the s, and basically, I mean, s is something between -2 to -0.7, depending on the measure arm. Nothing really spectacular. Okay. Then I find that, essentially, roughly speaking, modes which has angular scales larger than the causality scale, namely this relation, are basically stable, as you might expect also. But modes which has angular scale smaller, sufficiently smaller, become unstable. And the growth rate increases with increasing L number, the order. So again, it's like in the non-relativity case, the smaller scale structure grows faster. Of course, physically, you also reach, at some point, you reach the dissipation scale, and then it's a whole lot of questions that can only be answered with simulation. So that's basically what I find. So just if you want to see how it looks, so here, for example, is the distortion of the contact surface. So what I plot here is delta R over R of the contact. R is the radius of the contact, and delta R is the pressure. And you see that, and this is log of time from some t0. So you see that it grows exponentially, and it quite quickly reaches a nonlinear stage in a very short time scale. Okay. That's for the contact. And indeed, I find also, as in the non-relativity case, that the largest growth is at the contact itself. It then communicate the perturbation to the rest of the system, but essentially. This is the distortion of the shocks. And you see it goes much slower, but still, at quite early time, you get nonlinear distortions for these parameters. So, I mean, you do expect quite rapid growth and non-linear evolution quite early on.
What are you showing here exactly?
This is this is like this, just for the forward and reverse shocks.
Okay.
Okay? Because it's just, if you put it in this plot, you just don't see it. Okay. So the distortion of the shock becomes significant for sufficiently high order mode quite early on. And this is, for example, the evolution of the pressure. So what I see here is the delta P at the contact, just near the contact on two sides. And it's quite confusing because I normalized the drawing, so it actually follow each other just by pressure balance across the contact, but the normalization here is a side change. So anyway, you see that also the pressure grows quite fast, and this is near the contact. And here there is an exponential growth, which is quite significant for this mode. This is, I think I put the number, this I think is L over gamma is 100 here, something like that. And near the shocks I find it's much weaker. So I mean, you see that near the forward shock, this is the red line, the pressure perturbation are much weaker, but still it's significant for this parameter. And the reverse shock is distorted completely. I mean, you also need to expect this, right? So, okay, so this is what happens early on. Of course, this is the limitation of this model. I mean, I have this similar self-solved solution I don't know. So one question is what happens at late stages. So the conclusion here is that at least under these assumptions and these conditions, it's unstable and quite significant. So what happens at late stages? I mean, late stages we say that you enter the substratum in the key phase, you can forget about the contact, etc. And so this actually was studied by Gruzinov. So Gruzinov studied the stability of the substratum key solution, and you see the result here. I found that there is a small error in this paper. So this is the result I produced. But this error doesn't really change the result significantly in conclusion. Modified is okay. Just maybe it's a typo, I don't know. Okay. But anyway, so what you see that if you perturb the shock, the shock is stable, of course, but it's non-universal in the sense that if you perturb it, it decays but very slowly. What you see here is plotted. The evolution of the perturbation is plotted as a function of 1 over gamma squared. I mean, L plus 1 over gamma squared. And you see that it lasts for a very long time in the evolution. Yeah, so, I mean...
So, this is a strong perturbation.
No, that's normalized.
What's delta P over P?
No, sorry. What you see here is delta P over delta P at T equals 0. Just it just normalized to zero analysis. It's sorry, I mean that was just
Okay,
to
so one corresponds to the initial amplitude, that's
sorry?
what you're saying.
It's
One is
delta-
just the initial amplitude.
It's delta P over T over delta P over
Right.
That's what happens. So you see, here it sort of doesn't change because it's still acausal. So it doesn't talk, I mean, different region doesn't talk to each other. But then you find these oscillations, which, I mean, is basically similar to oscillation fine, but the oscillation decay, but they decay actually much slower than you might expect. So it's sort of, it's not quite clear whether the bottom of the key is really an attractor. I mean, eventually they decay, but as you see, until gamma reaches very small numbers. Okay, so my idea was that if you do distort the shock, and this is all speculations, I mean, that's my speculations, but it can be tested with full numerical simulations if you have some solution. Because if you early on distort the shock, as I see here significantly, I mean, you expect actually nonlinear distortion of the shock surface, then this is going to stay for quite a long time during the evolution of the shock. And then, then there is this process studied by Andy. It may be sufficient to generate vorticity and maybe produce magnetic field. And this is for speculation. It's a quantitative question. but that's sort of the idea. So also, if you distort the forward shock on sufficiently small scale, then I think you should be more careful when you do this. When you do the simulation of particle acceleration, it may have some effect. It's true that the scale may be still large compared to kinetic scale, but that's still, I mean, it depends on the dissipation scale, things like that. But it's something you want to keep in mind, at least. Okay. So what certainly is that if the instability is significant at early time, it's going to affect the reversion dramatically. So for this regime, so all these naive, of course, if, as Ellie said, if the ejecta is much hotter, if the reverse shock is ultra relativistic, then forget it. It should be stable. So then it's a question, what is happening, but it could be that the instability does develop, and then of course you should, you should take it into account when you want to construct models for the optical calculation and things like that. It's not clear that the naive models describe accurately what is happening. So it's something you want to keep in mind. Okay, so okay, that was Andres. So that's the final slide. So remarks. Actually, all of these remarks were made by Ellie during the talk, so we already discussed those. So one thing I think if the ejecta is magnetized sufficiently, I think if the alpha number is more than 0.1, it is stable. So of course, all these magnetic models, this is completely irrelevant to those. But it's not clear. There's actually one more point, that if the ejecta is magnetized but not too strongly, the instability may evolve, but then you mix the magnetic field in the ejecta is large, even if it's only 1% of equipartition there. So you not only amplify, but you actually mix magnetic field from the ejecta in this region. And so this is one point. Then, well, I maybe was too much. And then he said, if the reverse shock is, if the density of the ejecta is too low, I said then it's probably stable. Now, all these questions should be studied. Well, what I did is very naive. I mean, it took me some effort, but it's very naive in terms of what these guys are doing, sophisticated. But in principle, it can be done with numerical simulation. What you need is very high resolution, because the unstable modes have, L over gamma of, 100 and larger, something like that, or maybe 10. But if you want to see fast growth, you need to go to simulation to start early on with the ejecta, to go to simulation with resolution as high as you can. But certainly, the grid has to be certainly, you need at least 100 points inside and across. And yeah. So I think this motivates studies like this. That's all I can try and say. And this is very preliminary, so some is not much. That's it. Okay.